All right, welcome everyone to our talk about the security of some EV chargers or the communication modems inside them. So this should be a really fun talk with some cool demos for you. So just first of all, to get started, who are we and why do we feel qualified to actually talk to you today? So my name is Marcell. I'm a PhD student at the System Security Lab at the University of Oxford, and I'm doing my PhD on the security of EV charging. And in my work, I'm also supported by our colleagues at Arma Swiss who give us some technical expertise and funding. And in my spare time, I get to do basically the same type of research, except I get to work on the kind of more fun projects that can't necessarily be put into a research paper.
So my name is Berens. I work as a red teamer at Albertronic, one of the largest charger manufacturers in the world. And yeah, at night I do my own research. Most of it can't be publicized, and I do volunteer at different conferences like here as a goon. Some small disclaimers. Obviously the talk are on expressions. We do not represent our employees. And because of different NDAs, we can't go into all the details, unfortunately. Some of the fun stuff we can't share at the moment. And if you do your own research, please be absolutely careful and do some research beforehand so that you don't kill yourself when doing these kind of tests. EV chargers nowadays goes up to 1 megawatt. So it only hurts once, really quickly. So please be careful. We don't want our customers to send us videos of this accidents. And also, cars and chargers are super expensive, especially level 3 chargers. So ask for permissions. A lot of our customers also do pen testing of the products. So there's a lot going on of trying to secure these the ecosystem around it. Today, we will only focus on the 3 cable standards, CCS, CCS2, and NACS. CCS1 and NACS are most common here in the US, and CCS2 is most common in Europe. There are different other standards like MCS or GBT, but these are based on different technologies, and we will only be talking about these. These are defined in an ISO standard, really boring, long standard, so we're not going to go into details there. So how does electric charging work? So at the beginning, you obviously have the charging cable, and you have some basic signaling. So this is basically just a power signal, no real communication at all. And then after that, you initiate the power line communication. And after the power line communication is established, you have normal IPv6 network set up where all the traffic is being done. And after this is done, the actual charging starts. And today, we will only focus specifically on the power line communication, which is basically the same for every car and every charger which does DC charging. And as some background, how we ended up.
Yeah. So first of all, yeah, as we mentioned, you have this IP stack at the top, and there are a bunch of different versions for it. So we originally set out with a quest to kind of understand what's out there in the real world, how are the chargers deploying their software. But also, we were kind of interested in the power line communication layer. Again, even though the standard is pretty clear that you will just use this specific protocol for the power line, implementations can vary. We had a bunch of questions for how this might actually be out there in the real world. So what we did is we built an EV emulator box, which is actually this thing you can see here. It's not that big. And inside, what we have is essentially a Raspberry Pi, a power line modem, and a custom circuit board to just do some of the electrical signaling that the EV charging protocol requires. And what we could do with this box is we could go and plug it into real EV chargers via the charging cable. Again, back to safety, we are actually only connecting to some data pins. We are completely ignoring the power pins because I quite like being alive for now. So what the box actually does is it's running essentially the exact same protocols that the normal EV would. We implemented our own stuff in Python and C. And actually, the source code for this is public on my research group's GitHub. So we collected quite a lot of data points in the process, or we wanted to collect some data, and because we need to connect to real-world chargers, this meant we had to go on a road trip. So this started the week-long fun task of driving around Switzerland and looking at the mountains as well as the chargers. You plug the box in, and then it takes about 1 minute. It does a bunch of different charging sessions, and in the process, it basically figures out what exactly the charger supports and kind of some implementation details about how it works. It's doing all this in the same way a normal car would, so we're not actually going up and pen testing anything. So in total, we actually ended up going to 4 countries across Europe, and we got data from 397 CCS plugs in total. So we tried to randomize our data set a bit, kind of just going to places without specifically looking up manufacturers or anything. So we get a nice selection, and we got in total 26 manufacturers. We went to highways, big cities, small villages. We found devices that were made back in 2013, and we found devices that were manufactured in 2023 when we did our study itself in 2024. So with this, we kind of have a nice overview of what's actually out there, and we found a lot of interesting results about the protocols themselves, but for the purposes of this talk, we'll be focusing on the power line modem part of the communication stack. So our main finding was that all of the modems, or all of the chargers we could test, for some reason, you can actually ask it for a specific chip version of the communication chip and also the firmware. Just imagine the same for Wi-Fi. If I could just connect to your Wi-Fi, and it will tell me the exact chip you use and the firmware version of the chip. It's kind of a bizarre thing to do, but we can do it in the power line system. So what we found is that all the chargers use only 2 chips. They use the QCA 7000 and the 7005. And these are essentially, as far as we can tell, the same chip with some very minor differences. As for the firmware, we found a lot of stuff deploying firmware from 2013 or 2015. So over half the chargers have firmware that is more than 10 years old. Which again, I guess if you think about these like you would think about your Wi-Fi USB adapter, who really updates the firmware on that, as long as it keeps working? And then for our other finding, we specifically looked, because we know that there are in fact vulnerabilities in the power line communication system. My colleague Sebastian published, actually 2 years ago, it was a DEF CON talk, among other things, the broken wire attack, which essentially lets you wirelessly jam EV chargers, the wired communication. You can do it wirelessly with stupidly low amounts of power. And this was disclosed back in 2022, and it is something that we believe is probably fixable just in firmware. So we went out to see, do any of the chargers in the 2 years between the disclosure and our measurement study actually deploy some sort of new firmware? There's no charger, at least that we could find with firmware newer than 2022. So no one's actually patched this vulnerability. Right, so this is all starting to seem pretty interesting. Let's have a closer look at kind of how power line is actually used in the EV charging system. So you've got your charger, and then you've also got your EV. They're kind of running probably Linux or some other reasonably advanced embedded software, and they need to communicate with each other, and they do so via Ethernet. But they have these modem chips in the way, which convert the Ethernet packets into that waveform you can see on the screen, which really resembles a wireless packet for quite a few good reasons. It's basically the same modulation scheme as is used by Wi-Fi. I'll keep coming back to the Wi-Fi analogy quite a lot, because even though it's not compatible in any way, the technology here is very similar in some ways. And everyone's using just these 2 identical chips, which means that kind of any implementation flaw in them is going to affect the entirety of the industry. So logically, we wanted to kind of look more into the details here. And the first thing to do is kind of look up the data sheet, start to download the firmware image. Turns out they don't really want to give this out publicly. So there is no data sheet, and there is no firmware. For a while, they had it up on GitHub, and then they realized that this is probably a bad idea, and they removed it. Now, if you know how to use the internet, you might be able to find some files related to EV charging, but we're not going to give you any specific links. However, this PLC technology is actually the exact same thing you use at home. So if you've ever bought these Ethernet over power line adapters for use at home, Yeah, it turns out it's the exact same technology in the EV charging cable as well. Which means that for your home network, of course, they wanted to release a bunch of nice configuration utilities. So you can download the OpenPLC utils package directly from Qualcomm, and it's open source C, and it contains a bunch of tools to actually change the settings on these modems, do a variety of diagnostics. Now, in your home network, you will use a different chip. You might use something called the QCA7420, for example, but it's the same line of chips, it's the same manufacturer, so it's basically going to be the same thing. And so all of the tools actually just work flawlessly on the EV charging chips as well as the home use chips. So what can we actually figure out by looking at these modems and looking through the source code? The first major kind of finding was that the modems have something called the parameter information block, or PIB. So this is a large proprietary binary block. You can see the first few bytes of it on screen. And essentially, it is the settings file, but it doesn't really have any sort of metadata or key value pairs. Certain settings just begin at very specific locations inside of the file, called offsets in the technical documentation. So, for example, there's the MAC address, as you might expect. There's a manufacturer string. There's the network membership key, which, coming back to Wi-Fi, acts like the pre-shared key. And quite a few of these are settings which you might very well need to change in your use of the device. So the PIB can be read and written from the host system. You can send a special management message over Ethernet to the chip, and it will overwrite or give you back its configuration file. This is a perfectly normal feature so far, and the command to do it is handily provided in OpenPLC utils. You just provide the PIB you want to read and the MAC address of your device. Now, in the home usage, you have all of these power line modems plugged in around your house, and they form a network. And these are devices you've kind of installed in your own home, so you all trust them, you've enrolled them into the same shared network. And so they installed a handy feature where you can actually remotely update the other modems throughout your network. It's quite simple. Instead of putting in the MAC address of your own charger or of your own chip, you just put in the MAC address of one of the other chips. And what will happen is the packet goes via Ethernet to your chip, it will get modulated onto the power lines, and it will travel to one of the other modems which executes the command, which is all great in the home context. However, even though in the EV charging system, the EV and the charger form a Homeplug network, that's not because they inherently trust each other. That's just because forming a network is how you send packets between each other. So we asked, can you actually send this configuration override to an EV or to a charger via the cable? And this is how we discovered the PIB buster attack, which shows that yes, you absolutely can, which means that, for example, if you have a rogue EV, it can override the configuration of the charger, and likewise, a charger can override the configuration of an EV. And now you might ask, how bad can this really be? Turns out malicious PIBs can quite easily break a device because, for example, they can essentially tell the modem to stop communicating with the outside world entirely, both via the power lines, both via the host interface, just stop existing. And this is something you can easily upload via the charging cable. So we started doing some lab testing. We had a bunch of kind of EV dev boards, chargers lying around in our office, and we started testing the attack on them. And we found that it only works in some of the cases, but not all of them, which is a bit surprising because the firmware is always stock firmware from Qualcomm. They're not customized by the manufacturer. As far as we can tell, that's not possible. So the only difference between them can be the PIB itself. So this led us to the hypothesis that there must be some sort of security setting somewhere in this binary file. Problem is, we're looking at a 10 kilobyte blob of binary. We're looking for presumably just one bit, and we only have documentation or kind of ideas about 10% of the actual file. So the rest is unknown. So to do our investigation, the first thing we did was we got PIBs from one of the devices we had in our lab, which was vulnerable, which was a portable EV charger, as well as one which was secure, which was a dev board. And we compared the files, and turns out there are far too many differences between them, including the file size. As the firmware gets updated, they keep adding a few bytes to the end to kind of add additional settings. So the first thing we did is then we took these two PIBs, we truncated them to the exact same lengths, and we put them onto one of our modems. So now they are running on the same modem, on the same firmware version. The only difference between the settings is the actual configuration. So we created a little test setup, which consisted of a Raspberry Pi and then 2 of these powerline modems. They were both connected to the Raspberry Pi over Ethernet, and then they were also connected to each other over the powerline interface. So if we wanted to test how a specific PIB behaves, we could upload the configuration to it, or to one of our victim modems via Ethernet. Then we could get the attacker modem to pair to it over the power lines. And then we could start sending commands via the attacker to the victim. So we could ask, for example, the attacker to request a read from the victim, or we could ask the attacker to write to the victim. And then at the end of the test procedure, we also read the PIB back from the victim just to see if anything had changed on it. Because it's, for example, possible that it accepts the write command coming from the attacker, but it doesn't actually update its flash. So just by reading back from the flash directly, we could see if our changes are actually getting saved. So it is with this setup that we kind of started testing PIBs, and we found that, yes, the 2 PIBs we obtained, the secure one and the vulnerable one, are in fact behaving differently on the exact same hardware, on the exact same firmware. So the next thing we did to narrow down where the security setting itself is took the first half of the vulnerable one and the second half of the secure one. And we just kind of concatenated them together, really hope that we're not splicing over some important setting right in the middle, and just put this on one of our modems. And in this case, we found that it was actually secure, which means that the security setting is somewhere in the second half. And then we did binary search to kind of move this cutoff point, and with pretty-click, we narrowed it down to the byte at offset 1F8C, which if it's set to 0, it means that reading and writing via the power lines is allowed, and if it's set to 1, then it's blocked. So this is great. We kind of have an understanding of the attack now, but we don't know how prevalent it is really in the real world. Well, first of all, the dev boards we got, by default, they had it off, so they were all vulnerable. But for real chargers, well, we need to go out into the wild and see. So we went out back into the real world, started connecting to chargers again, and we issued a pib read command over the charging cable. And what this gave us is, well, we couldn't do a write, first of all, because that would be highly unethical. If something goes wrong with the write, we would be bricking now just people's EV chargers out in the wild. But thankfully, reading, as far as we can tell, is always going to be safe to do. Now, if reading was blocked, we just assume that the device is secure, because it's very unlikely that there is a sort of setting which lets you read, but not, or sorry, that lets you write, but not to read. So we just assume that those devices are all fine, but the devices where we are able to read, we then proceeded to basically check the security bit in the PIB, and then we also put the PIBs onto our test setup, so we're running the same configuration on real hardware, just in a lab, to validate how it works. So we ended up visiting 69 chargers in California. This is how it looks for someone in the security operations center of an EV charging company. Someone shows up to your charger with a backpack and plugs in a cable, and then walks on about a minute later. Don't ask how we got this. We got 69, so we went to 69 chargers in California, and we downloaded 41 PIBs in total. And out of these 41 indeed had no write protection either. So this is quite a bad ratio out there in the world. This impacts quite a lot of the bigger brands you might think of. So with this, we concluded that, okay, we have found something pretty serious. We understand actually what's going on, and we went to disclose to Qualcomm. So we sent them an email back in February of this year, and they actually got back to us and said, yeah, thanks, we are treating this as a vulnerability. It will be fixed. And for our perspective as academic researchers, that was kind of it. We wrote a paper on it. I'm actually going to present it next week. And it's kind of ended the story here for us. So how did I end up here at DEF CON giving a talk with someone working for one of the largest charger manufacturers?
Yeah, so we obviously also do our own security testing. And we found similar issues and also reported it to Qualcomm. And that was their response. First time ever when disclosing a bug is that they actually point us to other researchers who found similar issues. But how does it actually look like when trying to exploit this? So for this demo, we're only using the open source tools, not the NDA tools or our custom tools we created. So here we have one modem, connected to Ethernet 0, and connect it via power line to our attack modem. And so the power line communication is already established, so they can normally communicate via IP stack. So first, we look at the factory PIP, try to edit the security bit setting. Here, it is a little bit different offset than what was shown in the previous slide, because this is just a raw file, and we ignore the offsets mentioned in the NDA documentation. And then, as a last step, we flash the edited PIP with the security byte onto the modem connected to F0, and then look if the rewriting was actually successful, and by dumping the configuration file again and looking at the offset. And when then trying to dump or read out any kind of information via the attacker modem, which is connected to Ethernet 0, so the BCF2 is the MAC address of the victim in this case, and we can see that the security bit works and any kind of communication is blocked, as we would expect. But then, well, let's try to reset the device remotely. And in this case, we set the information request again to see if the security bit is still there, and then reset it. So even so the security bit is set, which should block any kind of requests, it still accepts the reset command. And when then trying to access the device information, you can see that now the device responds as if the security bit is not set. And you can then dump the configuration file, and you can see at the very bottom that now the security bit is missing. So what does this mean? So it means that on the chip itself, there's still, even if you flash your own custom configuration on it, there's still some hidden default factory setting, which basically falls back when resetting. This mostly works on devices where the Qualcomm chip is directly connected to an external flash. But with car manufacturers, for example, they mostly use something which is called host booting. So they don't have any external flash connected to it, and all the configuration is basically flashed on it via a host controller. And this means that at every boot of the chip, the device is reflashed freshly. So even if you do manipulate the flash in some way or the configuration in some way, as soon as the device reboots, it will automatically be reflashed to its original form. So in this case, there isn't really a persistent exploit to it, which we can share yet, but you can interrupt the charging sessions completely until the device reboots. So how does power line communication actually looks like? So here we have a normal signal graph of a common communication of the power line, and you can see there are gaps in between. This is actually because of hand radio frequencies. So they did know that there are a lot of other communication channels which might interfere with this standard. So there are intentional gaps in between, so it doesn't mess up any other kind of external communication. But how does it help us as an attacker? Power line communication is from 1 megahertz to 30 megahertz frequency, which is fairly high, which causes a lot of other issues, which is called common mode injections. So if you're familiar with it, basically every time you send a signal via a wire, no matter which kind of communication, there's a small electric field generated around the wire, which can be measured, and the higher the frequency is, the stronger the signal is. So how does this help us? So in development, you normally use, for example, from Vector, a device which is called a CCS listener, and you use an induction coil around, for example, the charging cable like here. This is a CCS2 cable, and you can read out the whole communication. It also does the decoding for you, but it's quite expensive. So this is round about like 3 to 4K. So it's not really possible as a normal researcher to get it. But so why don't we make the attack cheaper? So this is a normal development board. Unfortunately, also this one can only be bought B2B, so business to business. So even this one can't be bought like in a free market, but it does help a lot. So if you have some sources to do B2B business, this would be the way to start the research. It's around 280 bucks, so it's fairly affordable. And here I literally just connected the induction coil, nothing special, and I can still read out all the communication with some tricks. But, well, you can also just use a spare piece of wire. Again, it's a high-frequency communication, so the field generated by it is actually quite strong. So any piece of wire can pick it up. The Oxford researchers also publicized broken wire, which is done via an SDR. So you don't even need to connect it to the cable at all. Even with this cheap piece of wire, we got around like 1 meter distance without any amplification. So with amplifiers, there's pretty much no limit how far you can take it, depending on the environment, of course. But then we actually tried to replicate the broken wire attack in our lab, but the issue was above our lab there's a 5G antenna with all kinds of other antennas above, so there was too much interference, so we could legally test the broken wire attack. And we got it running, somewhat working, but we did have a side effect and we couldn't really pinpoint it. So one of our interns had the weird idea to let's hook the modem just to the ground terminal of the building and let's see if it works. And it does. And the reason behind this is the car and the charger make a so-called PAN system. So PE and neutral are combined. And therefore the power cable which goes into the charger shares the same ground as the car, which has a lot of attack vectors because you can now use any kind of ground nearby to the charger. So we literally stripped the isolation of an Ethernet cable, plugged it in a switch far away, and we're still able to attack the chargers or the car. Or you just connect to the screws of the wheel of the car, and you can still attack, because everything has the same ground. So there is no scope limitation for the attack, so to speak. And for the ground attack, if you don't use any kind of amplification, reading is quite difficult, but denial of service is quite easy to do, because power line communication is basically based on like a sliding window protocol. And if you fill all the windows, the communication can't work anymore. And therefore, it's quite easy to implant a rogue device somewhat near a charging park and basically hinder all kind of charging. And it's literally impossible to find a rogue device connected to ground. And yeah, so you can do a lot of damage with basically, no effort whatsoever.
All right, so for the final part of this talk, we've been kind of looking at these modems and using them at least still, with their stock firmware intact and kind of somewhat as intended. But we kind of felt that the chips themselves can probably do quite a lot more than what we've actually seen so far. So we kind of started to look deeper how the firmware actually works, what can we really make the chip itself do. So just start by examining the developer board. First of all, we actually have the QCA chip is actually the smaller one at on the bottom. And then we have next to it this much larger chip, which turns out to just be an Ethernet to SPI adapter I mentioned that the chips communicate to the host system via Ethernet. They communicate, technically they don't have the Ethernet hardware built in, so they just need this dumb media converter, but it's still Ethernet frames. But in the other direction, we also see the flash chip. So the chip connects both to the host via SPI, but it also connects to its own flash chip via SPI to download the firmware as well as to download the configuration. So if you want to kind of have a poke around the firmware itself, the logical first thing to do is to just dump the flash chip. Now, if we look through OpenPLC utils, we actually get a reasonably good idea for what to expect here, because they actually have quite a lot of code for kind of handling these firmware images and handling updates, even though they don't actually provide the firmware image itself. They at least have the code for how to do it. So what we're expecting to find is something called an NVM chain. As you can see here, it's a doubly linked list consisting of headers and then data blocks. They've got all sorts of checksums, a tiny bit of metadata. And so if we dump the flash chip, we're just expecting to see this. And actually, each chain even starts with a special data block called a manifest, which is very nice for us because it contains a lot of actual human-readable information about what the chain contains, what we're looking at, build dates, kind of version numbers, used for things like that. So all we're really expecting to find on this flash chip, it's only a 2 megabyte flash chip after all, is the firmware and probably the PIB, right? Well, let's see. First of all, if we dump the flash, right at the start, we find the exact kind of format for an NVM chain we expected, and it describes itself as a soft loader. So it has a soft loader binary part, as well as a flash layout section, which describes what else we can find on the chip. And what else we find is we then find an entirely separate firmware chain, which contains 4 small code modules, which I'm not entirely sure what they do, but they have kind of the names as shown on the slide. And then right at the end, we have the firmware section. And if you look into the firmware section, turns out it's an entire other NVM chain just nested there into the data block, containing a second smaller firmware section, and then a high entropy binary blob. Now, this immediately looked very sad to me because this means that, well, they're probably encrypting their firmware, and we've got the encryption system probably loaded by this small firmware block right before it. If we poke around the chip for some other stuff, we also find an area reserved for custom modules, which is entirely blank. I don't know what exactly you're supposed to do with it. The PIB, as we expected. Some scratch space, which seems to be used as its copying for like a temporary buffer. And then finally, an entire backup of the firmware. So from this, we can kind of start to get an idea for the boot chain. It presumably goes from the soft loader through these small code modules which initialize the firmware into the firmware loader, which actually does the decryption, and then finally into the encrypted firmware image. So the next step for us was to kind of start reversing this firmware loader and to see if we can do something about the encryption. So it's quite easy. This is still just normal ARM v5 instructions. And what it does is it, in fact, as we expected, it loads in the big binary blob from the SPI flash, and then it jumps into a function in the high F address space. Now, this is not in the address space of anything that the flash itself is getting loaded into. And if we do a bit more kind of digging, we can find that ARM itself uses an entry point very close by, also up in the high Fs. So this is likely the on-chip bootloader ROM code. Now, okay, let's try to look a bit more at this. We actually have code execution on the chip quite easily because on the flash, we have found a bunch of just normal machine code, and it's not encrypted. As far as we can tell, it's not signed. It's only the main firmware image itself that has some sort of protection on it. So if we override the flash chip, we can just get the chip to execute any code we want, which is great, but code execution on its own is unfortunately entirely useless because we actually need some sort of I/O. Now, we are dealing with a communication modem, right? So this should be very easy. It's full of I/O. We have PLC, which is great, except the PLC hardware is only ever initialized by the encrypted firmware, so I have no clue how to use that. We have Ethernet, same problem. We have GPIOs, also the same problem. The only peripheral I've actually seen so far in the non-encrypted sections of the code is the SPI interface to the flash chip, specifically reading. Writing is more difficult because of how write protection works on these chips, but at least we can read. So we stole a page out of the kind of attack that some of the CPU side channels also used, where we take the data that we want to send and we actually treat it as a memory address. And so we're actually issuing reads to the flash corresponding to, for addresses which correspond to the data we are trying to send, and the data we are trying to send is just to dump the entire bootloader memory address space. Of course, from the perspective of the flash chip, this does absolutely nothing because I'm just reading. But if I hook up some sort of logic analyzer, I'm able to sniff out the SPI commands coming from the chip, and from this, we could reassemble the entire bootloader. So now that we have the bootloader image, we can start reversing this as well. And this is where we start to find some much nicer goodies. So first of all, the bootloader already contains a bunch more hardware interfaces. So we have the SPI interface going towards the host system. So this is where the Ethernet packets go. We have even more information about the flash SPI. And finally, we even have evidence of there being actual Ethernet drivers in there. So some other variant of this chip supports directly connecting Ethernet to it, and the code is already in the bootloader, even on the ones which just don't have this as a feature. And we can also take a look at our mysterious decryption function. Yeah, it turns out that was just LZMA. It's just sufficiently high entropy that I couldn't see that it's compression instead of encryption. So with this, we are now actually able, for our next steps kind of going forward, to start creating proper C headers for the peripherals to figure out all the memory mapped I/O registers that the chip uses and kind of map these out nicely. And then also, with now the knowledge of how to decompress the firmware, we can actually start looking at it and decompiling the main firmware image. From this, we will then hopefully soon be able to kind of reverse engineer the interface to the power line section of the chip itself, which will open up the possibility of people creating custom firmware. Custom actual power line firmware that can do things that the original protocol couldn't, or just make some more secure or potentially hacking tools with it. So now that we've got code execution, there is obviously the mandatory question to ask whether it can run Doom. So let's just quickly review. We have very limited RAM and flash. To be honest, I don't actually know how much RAM we have because, again, no data sheet. There's also no operating system of any sort on this chip. There's no floating point. There's no screen or human input device. The only I/O we have is Ethernet. It's dark and we're wearing sunglasses. So the short answer, yes. Yes, we can. So we created this simple demo. We've got the dev board here, and it's connected to the computer via Ethernet. And then as I plug the chip into power, it starts booting up, and it will open up a UDP connection to the host computer and start sending back the frames. And yeah, there they go. And so this is like a somewhat custom version running live on the chip. So in this demo, the chip is just sending back the frames via UDP, and I'm sending in the raw keyboard and mouse also via UDP. So no real processing is happening on the computer itself. And then as we unplug it from the power, the frames stop coming. Right.
All right. So as you see, the firmware on chip currently is quite broken because you can basically do whatever you want if you put in the effort. One of the main issues for researchers is the NDA issue. It's security by obscurity, and as everyone knows, it doesn't work. As soon as you get your hands on one of these chips, it's super easy to reverse it, and with the help of all the other publications and researchers who have publicized in the past, it is super easy to reverse the whole protocol stack as well because it's customized, so it doesn't help at all to hide behind any kind of NDAs. There is a little bit of public stuff released by Qualcomm itself, but it's a bare minimum, and the complexity is so high as well, it doesn't really make sense to hide it. On the other side, for the signal leakage attacks or the attack vectors, you could use, for example, shielded cable. But again, since it has the same ground, because the shield has to be connected to something, and in most cases, shielding is always connected to ground. So it doesn't help to use a shielded cable The only thing which kind of helped doesn't involve a lot of work is, for example, adding ferrite cores for the input wires. But again, the ground of the car and the charging station itself is also exposed. So even that doesn't really fix the issues. And then, yeah, there is no security when it comes to the Slack protocol, which is used to actually establish the power line communication. The key is transmitted in full clear text. So as soon as you can sniff the key via different methods, for example, the leakage of the signal, you can intrude into the network and manipulate freely whatever you want. And as we also shown, even if the security features are enabled, you can simply bypass it. And at this point, there's no public patch available for these issues. And there's also no publicly available timeline when this will be fixed. And the main issue, as shown beforehand, a lot of the chargers and the cars are running on ancient firmware. So even if there's a fix publicized this year or next year, it will take a decade at least that the patch is actually rolled out to all the devices, if we're lucky. But this also means, as long as there are vulnerable devices, we need a downgrade version or possibility that the old devices still work. Because if you own an EV and tomorrow you can't charge anymore, you will be pissed, right? So there will be the need of like a transition phase, but in automotive and industrial devices, these phases take forever, as many of you know. So let's see what comes next. And my personal opinion is we should keep PLC where it belongs, in your home network, not for industrial devices, not for critical infrastructure. In my opinion, it's broken beyond repair because there's no easy fix for it. And even if there would be a fix, we will have to drag vulnerable versions for years to come. And so, yeah, let's see how the whole industry goes with these findings. And yeah. Thank you for your attention. So on the slide deck, which is also publicized on the media service, we put some references. And with the help of AI, using these resources, it is super, super easy to even get the functionalities which are hidden behind NDAs, just an FYI. Yeah, any time for questions?
All right, give it up. Congratulations, track 3 on the runtime. Very good.